I hope you enjoyed that video series on SAP HANA Spatial so far. This is the last video of the series, and I want to conclude what we've seen before with one conclusive example, actually getting everything together that we have learned so far. So the demo will be about a house prediction. If you see that house here, what do you think what the price of that house would be? Because you have no clue, because you're missing information. So I'll give you some information. That is a detached house. It's built in 2001, 500 square meter land size, 200 square meter living area, and 5 rooms. Do you now have a better idea of what the price of that house might be? Maybe, but maybe you have the feeling that you're missing information because, as everyone knows, high house prices are heavily correlating with the location of the house. So that house is close to the seaside. It's 20 minutes to commute to work, 10 minutes to go to school by bike. Basic groceries are around the corner. There's a supermarket 5 minutes by car and a few restaurants in the neighborhood. So whatever you thought before, I think that price went just a bit up because it's close to the seaside, where everybody knows that's an indicator for a high price. But what if I tell you the best thing about the house is that it has an excellent connection to the airport? Right. You have to know everything. You have to know the non-spatial features and you have to know the spatial features to actually come to robust and precise prediction. And this is exactly the setting for our demo now. So I took an example data set, which you find online with almost 35,000 housing prices for the city of Melbourne from years 2016, 2017, and 2018. I augmented that data with OpenStreetMap point of interest data to understand the neighborhoods of the different house listings. And for the demo setup, I used the HANA Cloud trial instance. I used Jupyter Notebooks for interacting with that instance, and I used Folium for visualization. If you want to read that all instead of watching the video, you can also visit my blog, which you see linked down there. Good. Let's jump to the Jupyter Notebook. So first of all, you see my HANA Cloud instance running here. It's a trial instance with 30 gigabytes of memory, which is more than enough for the example we're going to look at. So this is the notebook. I'm just going to restart the kernel, clear the output, so that you believe me that everything that you see here just works on a vanilla HANA Cloud trial instance. There's really nothing that you have to prepare if you want to do it yourself. You also find that notebook online, by the way, linked in the blog, which I have just shown. So what you see in the demo is that we upload a CSV file containing spatial data to HANA Cloud. We're training a regression model only incorporating the non-spatial features, and we're trying to predict the price of the house, and we'll see how that works out. Next thing, we retrieve and upload OpenStreetMap point of interest data for the respective area we're looking at. We compute spatial features for enhancing the training data set of our machine learning model. And we're going to train the exact same regression model as before, incorporating both the non-spatial and the spatial features so that we have the 360-degree view on the records or on the housing prices that we have there in the training data sets. Afterwards, we're going to compare both models. What we do as a cherry on top is actually that we predict the price of a reference house. So what we'll do at the very end is we fix all the non-spatial features and move one reference house across the city of Melbourne, and we see how that influences the price. So how only spatial features can influence the price of the exact same house. Let's start over. So preparation, we're importing everything that we need in Python. Just to briefly go over that list. So we're using pandas and geopandas for the data handling in Python. We just use some helper libraries to get the password and everything from files so that you don't see my password here in the Jupyter Notebook. For database connectivity, we're using SQL Alchemy and its HANA plugin, which is actually a very convenient way of issuing SQL statements from Jupyter Notebooks. We will use the library OSMNX to download and import OpenStreetMap data. For visualization, we're using Folium and Shapely. For the machine learning, we're going to train an XGBoost model and use the SHAP library to visualize the impact of the different features on the machine learning model. So first we're setting up the database connection. Again, since this is a HANA cloud instance, we have to make sure that we use encryption. So we set encrypt to true. I'm just loading user, password, host, and the port from a file. Now we're connected to the database. We're just setting some configurations for the SQL magic. And now this is actually the first time that you're seeing SQL statements here. So if you're not familiar with SQL Alchemy, it essentially gives you the ability to issue an SQL statement the following way. So you have just percentage SQL to indicate that the following will be an SQL statement. Then I'm saying drop table Melbourne housing. This is interpreted as an SQL statement and it's sent to the database connection that are configured up here. So this cell is just to clean up old demos that I may have run on that instance before. Good. Our data, or for our analysis, we will use the spatial reference system 28355, which is a planar spatial reference system, which is suitable for the area of Melbourne. If the spatial reference system is not yet installed on your HANA Cloud instance, which is the case if you have just a fresh HANA Cloud trial, then we need to issue the statement over here to install that spatial reference system. So create predefined spatial reference system identified by 28355. As you can see in the metadata, this spatial reference system is already predefined. That means HANA knows the definition of 28355 and just installs it from the internal metadata. For my instance, I've used that demo before. That spatial reference system is already existing. So you only need to do that once for each instance. Good. So we have some helper functions here to generate maps, which I will just quickly skip. We will use that later to just get some visualizations. Also, we're using some helper functions for handling the machine learning models. So we have one function to train the model, one to do a prediction, and to explain the model. Good. Now we're uploading the CSV data. I already downloaded that data set from Kaggle. I put it to that folder and now I'm importing it to Pandas data frame. And this is what the raw data looks like. So you have here different housing sales and you have a latitude and longitude in there, fortunately, and somewhere there is a price for that house. Good. We're adding some fields like the ID, and we're also converting the date column to a proper date format that HANA can interpret. And we're removing each column of the data set, which gives us a spatial indicator. So we only want the latitude and longitude in there and nothing else. So for example, suburb, address, distance, postcode, that all can be used as an indicator for geospatial location. So we're removing those. See what the data set looks like now. Good. So it's less columns than before, and we have that artificial ID that we can use. Now we're doing the upload to the HANA trial instance. This takes a few seconds. After less than 10 seconds, that's finished. Now we got on the database level one column latitude and one column longitude. However, we learned before that to handle geospatial data on HANA, we need a column of type ST-geometry, which is created from the latitude and longitude values. Also, we learned before that when we use a planar reference system, our computations get less complex, so it's more performant to do that. So we're adding a column called shape of type ST-geometry and SRID 28355, what we have defined before. And we're setting that column with a value stgeom from text. Here we assemble the well-known text representation from latitude and longitude. By the way, the typos here are in the original data set. They're not mine. I insist on that. This is in spatial reference system 4326, but we're doing a transformation to 28355. So we converted all 35,000 listings and we have created proper geometries. Maybe this is the time to look at the database level. Look here into the trial user schema tables. We should see the Melbourne housing here. Maybe let's do a refresh because I'm still seeing tables which I've created earlier but dropped meanwhile. So you see here the Melbourne housing, so no OSM data. And we can view the data in there. And you see that at the end we have a proper geometry column showing us locations in the city of Melbourne. Good. Now we're creating one view which just casts the data types and will help us to actually properly transform the training data that we have. So this is the Melbourne housing predict view. Let's look at the records per year. You see that for the year 2016, we got 6,400 records. For 2017, we got around 12,000 records. And for 2018, we got 2,600 records. So let's train our first regression model, the one without the spatial features. So we're selecting the training data into the data frame housing. We're simply issuing select star from Melbourne housing predict view. So we're now getting all the 35,000 entries to the client, which lasts a few seconds. Now the data has arrived. So we're creating dummies out of the features so that we only have categorical features for the machine learning model. And we're determining the dependent variable for the model, which is in that case the price. Good. Now we're cutting training and test data. I'm going to use the data of 2016 and 2017 for training and testing on the data of 2018. So for training the model, I leave out the 2018 data and I apply the model to the 2018 data to actually measure how the performance of the model is. So I'm training the XGBoost model. Model's trained already. And now I'm looking at the median absolute error of that model. So on the training data, I can see that I have a median absolute error of 220,000 Australian dollar. Whereas on the test data, this is slightly worse. I got around 300,000 Australian dollar with a median absolute error. You have to know that the average price of the houses in the data set is something between 900,000 and 1 million Australian dollar. So we're off something like maybe 25%. Good. When we explain the model, we get that nice SAP visualization. So what this is indicating is you have the feature with the highest impact on the model at the very top. So the highest impact for the price in our model is the building year of the house. And you see here that high values of that feature, so this is the red color, correspond to a negative price or to a negative impact on the price, whereas low values correspond to a high impact of the price. To put that in other words, that means that older houses tend to be more expensive, whereas younger houses tend to be cheaper. That sounds counterintuitive. However, if you think about the situation where older houses are usually located, they're usually in the center of the city. Younger houses are usually in the suburb of the cities in development areas. So what we see here may be the fact that the geospatial dimension sneaked into our model, although we eliminated all the geospatial features before. My hypothesis in that case is that the year built of that house just acts as a proxy for the location, and it tells us that houses in the city center are more expensive. My hypothesis, I can't really prove that. The rest of the features is like you would expect. So the more rooms you have, the more expensive the house is. The more bathrooms you have, the more expensive the house is. The bigger the area and the size, the more expensive the house. That all kind of makes sense. Now let's upload some OpenStreetMap point of interest data, which gives us some context on the houses we see here. So the first question is, what OpenStreetMap point of interest data do we load into our trial instance? It will take us a while to just upload all the points of interest of the world, and probably it's also the trial instance won't be enough for that. So we're issuing one statement to ask for the convex hull of all the data that we have in there. So we're actually looking at the locations of the houses, and we're just querying the area where these houses are located. If we get that on a map, we'll see that this is the area that we're talking about. So also we only need to load points of interest inside that area. So as I said before, we're using OSM and X to do that. And now we're actually downloading the points of interest. So due to the network connectivity, the downloading to Python lasts a few seconds.
So I'm going to fast forward that in the video. I'm still waiting, but remember that this is just the download from the internet to the client.
There we are. After 40 seconds, around 50,000 point of interest for that area have been downloaded from the internet into the pandas data frame that we have here. So this is what the data looks like. We got different attributes actually describing what kind of point of interest that is. And we have a geometry in there, which actually is a well-known text which defines the location. Now we're uploading that data to HANA. Like we've seen before, we use pandas to do the actual upload with the toSQL function that we have here. After uploading the point of interest data to HANA, we enhance our table with a shape column of type stGeometry and the spatial reference system that we want to have. And we're generating the geometries out of the well-known text that we have here in the data. So that's the well-known text, and we use the function stgeom from text to convert that well-known text to a HANA geospatial format. So now we have everything on HANA. We have the points of interest as well as the house listings itself. Now we're going to calculate some geospatial features. So first of all, we remove the suburb in the very beginning, if you remember that. We want to create something data-driven, which gives us a proxy for something like a suburb, because as you know, the price of a house might as well depend on the suburb where it is located. There are expensive regions and there are less expensive regions due to different reasons. So what we use here is that we do k-means clustering of 30 clusters. So we want to divide the city of Melbourne into 30 different regions based on the point data that we have. We calculate the cluster cell of each k-means cluster, which corresponds to the Voronoi cell of its centroid. So when we visualize that on the map, we see nicely that we got a number of clusters in the in the center part of the city, and we roughly have one cluster per big road going outside of the city. So here, around here. These cluster IDs, for example here cluster ID 12, we will use as a proxy for the region or for the suburb. Next thing is that we're incorporating the points of interest. So I'm going to group points of interest. For example, I have one group here. If it's a bar, restaurant, cafe, fast food, pub, barbecue, theater, cinema, or nightclub, I call it an entertainment point of interest. The same I'm doing for health, education, childcare, community, emergency, groceries, shopping, and the airport. Because that example we had before, right? So let's, for example, create a heat map of the entertainment points of interest in the city of Melbourne. So I'm now retrieving the entertainment points of interest from the database, and I use Folium to visualize that on a heat map. So what you see here is that the center of the city, you obviously got a high density of points of interest of type entertainment. This is what we would suspect. If you zoom in here, you clearly see the central business district as an area with a high density. But also you see here Brunswick Street in Fitzroy, where you have all the music clubs and the bars. You see here Lygon Street with its restaurants. And down here, if you're familiar, you see some higher density in Chapel Street. Good, so that seemed to work. Now I'm again using the Voronoi cells to determine the closest point of interest of a certain type to a certain house listing. So I'm asking, for example, given a certain house, what's the closest restaurant? Or how far is the closest restaurant? Or how far is the closest shopping location? So I'm using Voronoi cells for that by just spanning a Voronoi cell around each point of interest and looking at the houses that are within that Voronoi cell, so that are closer to that point of interest than to any other point of interest. And I'm doing that, of course, per group of point of interest, which I determined before. I'm doing the same thing with the density of points of interest. So with the first view, up here, I can ask what's the closest restaurant or how far is the closest restaurant. With a second view, I can ask how many restaurants I got within a certain area around the house. So I can give that here as a parameter, the distance in meter. For example, I can ask what's the number of restaurants within 1 kilometer around that house. That helps me to determine if this is, for example, a nightlife area or not. One other thing that may be interesting is to somehow get a sense of the distance to the city center. But as you may know, the city center in typical big cities is not one point in the city, it's rather an area. So for that reason, I've drawn the central business district as a polygon, which you see here. And the second thing which I've drawn is just the seaside, because this is something which also may be interesting. So we can now measure the distance of each house to that central business district polygon, as well as to the bayside. So I inserted all that data of that two data sets already in the table Melbourne area of interest. Of course, I'm free to add more areas of interest if I'd like to. For the moment, we stick with that. Now the interesting part, we're training a regression model incorporating those geospatial features. So we have the non-spatial features that we had before, plus now we have the geospatial features. So this is the view that I'm using to actually prepare that data. Let me go over the features. So what I have here is the distance to the central business district and the distance to the bay. I have the region proxy, which I created using the k-means clustering. I have the closest distance to each kind of point of interest, and I have the count of points of interest of each kind. So, for example, how many entertainment locations are around the house. You see in the join down here that I'm querying an area of 1000 meters around each listing. Good. Now I'm querying that view and load the training data into Python again. So as I'm doing the data preparation, I'm transferring those 35,000 entries. Again, this lasts a few seconds.
And if it's too long, I'm going to fast forward that again in the video.
So in my case, after 30 to 40 seconds, data has been prepared and transferred to the client. Again, I'm creating the dummies, I'm creating my dependent variable, I'm splitting training and test data set like I've done before. I'm training with the years 2016, 2017. I'm using the test data of the year 2018. So it's exactly the same setup as before. Again, I'm training my XGBoost regression model, which is finished after a few seconds. And if I'm looking at the median absolute error, I can see that the median absolute error on the training data set is 136,000 Australian dollar. On the test data set, it's even slightly better. It's 127,000 Australian dollar. So when we explain the model similar as before, we can see that the feature with the highest impact is a geospatial feature now. So before, when you remember, we had the year build. The year build is now on the 7th position, which somehow underlines my hypothesis that this was just a proxy for the geospatial location of the house. The geospatial feature with the highest impact is the distance to the central business district. So the closer the house is to the central business district, the more expensive it is. That makes, of course, sense. The next most impactful feature is the number of rooms, which is a non-spatial feature. The next most impactful feature is the distance to the bay. So the lower the distance to the bay is, the more expensive the house is. And we have some other geospatial features down here, like for example, we have different regions. There's region 26, where a high value, so region 26 is a binary variable, it's either 0 or it's 1, depending if the house is in there. And in our case, a high value of the variable clearly indicates a higher price of the house. That means region 26 is an expensive area. If we look at region 27, it's quite the opposite. A high value of that variable indicates a low price of the house. So region 27 seems to be an area with lower prices. So now let's compare the models one by one. To just set that into relation, the median price of the houses overall in the data set is what I mentioned before, 910,000 Australian dollar. When we now look at the different models, we see that on the test data, our first model was on median absolute error something like 300,000 Australian dollar, whereas the second model incorporating the geospatial dimension had a median absolute error of 130,000 Australian dollar. That means that for the non-spatial model, I'm off more than 30%, whereas for the spatial model, I'm off only 14%. So that's an increase of nearly 20% when I compare the error ratios. When I now look at not only at the precision, but also at the robustness of the model, I can see that the deviation between train and test for the model without the spatial features was 25%. For the model with spatial features, it was only 6%. And if you remember, the test, applying the model to the test data set was even slightly better. That means, again, we got a 20% increase in prediction robustness. That looks pretty good, right? As I promised in the beginning, let's just do one exercise and set a cherry on top. So we're predicting the price of a reference house to exactly isolate the influence of the geospatial dimension on the housing prices according to our model that we trained. For that, I'm replacing my training data that I had with training data of one reference house. So I have here a hexagonal clustering, and I'm using that standard house, which has 3 rooms, 3 bedrooms, 2 bathrooms, 2 car parks, 600 square meter land size. So pretty much the average of the data that I see here. And I move it to the different hexagonal clusters over the city of Melbourne. So I got 75 hexagonal clusters in X direction, and I'm just placing it in the very center of the cluster, which I do here. So I'm using stclustercell.stcentroid as a location for the house. So now I'm retrieving the data, and I'm using the data now. That means I have the non-spatial features fixed and the spatial features move over that hexagonal grid that I defined. I'm creating the dummies again, and very similar as before, I'm training my model. And I can see now that for the exact same house, the minimum predicted price of my model is 300,000 Australian dollar, whereas the maximum predicted price is 2.5 million Australian dollar for the very same house. Now, to visualize that on a map with Folium, I just show my hexagonal clusters, and the color coding shows the price of the house within that hexagonal cluster. So I can see over here is the central business district. You see the red color over there. That means that is more expensive. Also, it clearly indicates that the hexagonal clusters on the bay seem to be more expensive. So if I take that, for example, my reference house is going to cost 1.6 million Australian dollar, whereas I take that cell over here, my reference price is 530,000 Australian dollar. And even if I move far away from the central business district, down here Frankston East, so that's 40 kilometers from the business district, the price of my house is almost 2 million Australian dollar. So why is that? We've seen that the central business district is actually, the distance to the central business district is the most indicating factor. I thought that it was an outlier, and I actually checked out on Google Maps. And if you see the very same location down here, so you have here, what's that called, the Nepean Drive. If you go to the same location on Google Maps, you actually see that this indeed seems to be a pretty expensive area. So if we had houses there in our training data, I'm sure they were expensive. With that example, I'd like to conclude this part of the demo. Maybe if you ask me, or if you've seen all the videos before and you ask me what is the takeaway of the videos and of that demo, I think it's really one thing. If you're doing analytics, if you're doing machine learning, if you're dealing with business data, you should consider the geospatial dimension. There are some specifics which you need to know about it, but it's worth the effort of doing it. And there are tools out there like the spatial engine of SAP HANA, which actually make it pretty convenient to handle that kind of data. If you carefully watched all the videos of that series, you'll reckon that the window behind me got pretty dark. It's late at night for me, and I think it's time to call it a day and to celebrate my personal Devtoberfest. Have a happy Devtoberfest yourself, and if you want to know more about HANA Spatial, follow me on Twitter. See ya.